Welcome to this screencast for the course Applied Economic Analysis. The idea of the screencast is that I'll guide you through the notebook for the course, which you can find on GitHub at this address. I'll not be giving exactly the answers to the notebook, but I'm going to give you enough guidance and tips for you to actually solve the notebook by yourself. So we're going to start with the section the market and the subsection why do we as economists tend to love the market. And the problem we're going to analyze is actually fairly simple, and it's simpler than the one in the notebook. We're going to be looking at the case where there are 50 consumers and we're going to have 10 units of a product. Each consumer wants to have at max 1 unit of the product, and consumers differ in their utility for a unit of the product. So the first thing that we're going to do in Python is to generate a vector of utilities or valuations of the consumers for a unit of the product. Now there are a number of ways in which we can do this. So one way in which we can do it is to use NumPy arrange. And certainly when you're starting with Python, it's a very good idea when you start using new commands to have a question mark after them and then evaluate the cell. So shift enter in a Jupyter notebook, and it will explain to you how the command actually works. So in this case, what we see is that you can give it a starting value, which is optional because it's between square brackets. You give it a stopping value and then the step. So in our case, we could start at 0. We could go, let's say, to 100, and we're going to take steps of 2. So that's going to give us this array of valuations where the first consumer has value 0, the second consumer has value 2, and the last or 50th consumer has a valuation of 98 for this product. So this would give us a deterministic set of valuations, but most of the time it's easier actually to work with randomly generated valuations or utilities. And in NumPy there's a way to do it, and there are other packages as well. So let's first look at NumPy. So NumPy has a random library, and we would, for instance, be interested in a normal distribution. So what does the command look like? If you want to use the normal distribution in NumPy, you first specify the location or the mean or the mu of the normal distribution, then the scale or the standard deviation, and finally you would give the size of the vector that you want to have. So in our case, that would mean that we're going to have draws out of a normal distribution, let's say with mu equal to 10, a standard deviation of 2, and we need 50 units. 50 samples out of this distribution. So this would be the result that we would get. So these numbers are randomly drawn. They're not ordered. So it's not the case that this first element is the smallest one, the last one is the biggest one. They're just random draws. Another library which can also provide us with random numbers is TensorFlow. So then we would do TensorFlow random normal, and again we can give a question mark. And now we see that the syntax is different, because now we're supposed to first give the shape. So we need 50 units, then the mean, and then the standard deviation. So let's do that. So we give a one-dimensional array with the shape of what we need, which is a 50 units, one-dimensional with 50 entries vector. We're again going to specify that the mean is 10 and the standard deviation is 2. So in TensorFlow this gives some additional clutter which is relevant for TensorFlow but not necessarily for us. So one way to get rid of this is to specify that we want to have the NumPy version of this array. and then it looks a bit better. Now actually what we need is we want to have this thing sorted. So we want to have a NumPy array we want this thing to be sorted, and for reasons you will see later on when we start to use slicing, it's useful to have this sorted in a reversed way. And you see we get an error message where Python complains that there is suddenly an end of line where actually it doesn't stop. So we need to add another bracket here. And if you run it now, we actually do get an array that is sorted. So the biggest entry is the first one is 13, and we go to 12.7, then 12.19, etc. Yeah, so this seems to work. So let's call this our vector valuations. And we're going to run this. Now the best we can do in this economy is to make sure that the utilities that we are going to realize is going to be valuations, and we're going to give these products to the first 10 consumers because these are the ones with the highest utility for the good. So we're going to use slicing notation here. So we say to Python, out of this vector valuations, give us everything from 0, from the first index up to index 10, but not including index 10. Yes, so because we start at 0, we actually get 10 units out of this, which you can see if we look at the length of utility realized. Yeah, so you see that indeed utility realized has 10 entries. So now we can calculate what the welfare is in this economy. So the total sum of utilities that are generated by this way of distributing goods or allocating goods to my 50 consumers is the sum of this vector utility realized. Oops, and for later reference, we can actually print the outcome. So we say welfare equals. We're going to format this to make sure that we don't get too many digits. Point to F. Format this thing called welfare. Yeah, so in my case, but it will be different when you run this because all these numbers are random, the welfare that we're generating in this economy is going to be equal to 133. Now just if you're wondering what is the optimization problem that we solved, if you're sort of mathematically inclined, the optimization problem that we have solved here is that we have this variable xi, which can be either 0 when a consumer does not get a unit of the good, or it can be equal to 1. And then the thing that we're maximizing is the sum, and let's use Python notation here in terms of how we count. So we start counting at 0, then we go all the way up to 49. Oops, this should be xi times ui. So ui is the utility of individual or consumer I that he gets if he gets 1 unit of the good. So when xi is equal to 1, that means individual I gets the good. We're going to realize this utility ui. If xi is equal to 0, then we don't generate utility for individual I because that person doesn't get the good. So now we have a constraint, so we use Lagrangian. And the constraint is that when we sum over all the individuals, all the way up to 49, xi, this cannot exceed 10. So now if we look what this looks like, you see that the optimization problem that we have is that we're going to choose xi, which is either 0 or 1. So we either give the good to individual I or we don't. We maximize over the 50 consumers that we have in this economy. And the total resource constraint is that we cannot give away more than 10 units of the good. Now the question for you is, what is the Python equivalent of the Lagrange multiplier lambda here?